Okay, we're going to do two more examples of tension problems right now, okay? And these like border on conceptual problems just to kind of more wrap your head around how tension works and how it can be applied in certain situations, okay? One of those situations involves a painter on his own pulley, okay? And this is a little trick that painters have learned to devise, right? Especially back in the older days, where you had a painter, right, that was on like a little platform that he made, right? And there he is, right? And there's his little hand, and he's got this rope, right, that he's holding onto, okay? And the question is, so he's applying a little force on this rope downwards, right? Some force he's applying, right? Now, the question is this going to mean in order to lift himself up, he needs to pull his weight, less than his weight, or more than his weight, right? And you can probably guess that if he's going through the effort to do this little contraption, he's probably going to be pulling less than his weight. This has got to be a benefit to him. But why? Why does this work? Okay, so here we go. We have a tension from this string pulling up on him here, right? But if he's pulling on this rope, right, the rope's pulling back on him with an equal and opposite force, right? So this tension here, there's actually two of them. And it's equal to the force that he's applying. Okay? That has to be true from Newton's second law. Whatever force he's pulling back on, there's going to be a tension pulling back that's equal to it. And the tension everywhere in a string is equal, assuming that it's a massless pulley, but we're going to simplify that. So that means that there's two tensions from this rope and this rope acting on his hand. Okay? And of course, we still have his weight going down. All right. So what does this mean? Well, let's do a quick Newton's second law. Summation of forces in y equals MAY, right? I want him just to be able to start accelerating, so we're going to assume that that's close to zero, basically zero, right? Like what tensions, what forces they have to pull so he just overwhelms his weight? Well, that's going to be zero. And in this case, we have two tensions up, right? T plus T minus the weight going down. So we have 2T minus W equals 0. That means that T is going to equal W divided by 2. And T, remember, is the force that he's applying. Okay? So in this configuration, the painter only has to pull half his weight to lift his full weight. And that's kind of the magic of a pulley, okay? And why they're used so often. So this is more on the realm of a conceptual question, explaining why a painter pulling himself up like this is actually going to have to use half the force that someone would have, that an elevator would have to use, for example, to lift him up. Okay. All right. So if you guys can go to the next slide, I want to talk a little bit about an Atwood machine, right? Which is, kind of like a pulley system without a human. All right, it's basically just two objects with two different masses that are hanging from a simple massless pulley. Okay, and the question is, what would be the acceleration of a system, right? Depending on what are the masses of the two different parts of the pulley. Okay, so let's take a look at it. We have a pulley system here, right? Okay, and we have a mass on one side. We're going to call it M1, right? And over on the other side is another mass. We're going to call it M2, right? And we're going to say that M1 equals 5 kilograms. And we're going to say that M2 equals 10 kilograms. Okay, and we want to know what the acceleration is of this little system. Okay, first of all, let's just predict. In which direction is this guy going to be accelerating? Well, M2 is a bigger mass, right? Which means it's going to have a bigger weight. And so we expect this is going to be, M1 is going to be sliding up while M2 slides down, right? And it'll be an acceleration, right? Because, presumably this force acting on this guy in this direction is going to be bigger than this force acting on this guy in this direction. So the net force will cause an imbalance, right? But how do we find out precisely what that acceleration is going to be? No big surprise. Newton's second law is going to come to the rescue. And here's what's happening. We have this guy, this M2, right? We have to draw his free body diagram. Well, what's going on? We obviously have a tension going up. So I have tension here in this direction, right? What's going down? Well, I, of course, have this guy over here being his weight, right? So that's going to be, we'll call that weight 2, or just M2G, okay? All right, let's draw the free body diagram now of this guy, okay? We have a tension going up. For now, assuming a massless pulley, these tensions have to be equal, right? And he is going to have a weight 1, which is M1G, okay? So now I have two different objects, okay? And I want to do a Newton's second law analysis for both of them, okay? At this point, you don't necessarily know why you have to do one for both of them, but we're going to see, okay? For now, I'm just going to say it never hurts to give yourself as much information as possible, okay? And so if you have two objects that are both part of the same motion, right, then you want to get yourself as much information as possible. You want to give yourself the best chance to answer the question. So let's analyze both of them. So this is for M1 over here. This is for M2 over here. Okay? All right. We have, again, summation of forces in Y equals MAY. And we got summation of forces in Y on this guy equals, this will be M1, obviously, and this will be M2 AY. Okay? Now, a couple things that I want to point out here. I didn't do summation of forces in X. Why not? It's not necessary. There's no forces going on in the X direction here, right? This is a Y situation, right? We're all dealing with a Y situation. So we can just leave that away and focus completely on what's going on in Y, okay? All right. Starting by our summation of forces on M1. Well, we know we have tension pulling up, right? And we have weight going down, so minus M1G equals M1. I'm just going to call it A because these are the same acceleration. These are connected by the same rope, so A, the magnitude of the acceleration, has to be the same. Okay? So now I have my one equation down. Okay? The only thing that I know here is M1, which is 5, and G, which is 9.8. T and A are both unknowns. Okay? And this is why we ended up doing the analysis for both. I have one equation and two unknowns here. I need to get another equation in order to be able to solve two equations, two unknowns. Okay? So let's do this. We have summation of forces in Y. What are the summation of forces in Y for M2? Well, we have tension again. Again, it's the same T. Okay? Has to be the same T because they're part of the same rope. And the tension in two parts of a rope aren't going to be different if there's a massless pulley here. Okay? And so then I'm going to say minus M2G, right, minus that weight, right, equals, now here's something tricky. This guy is accelerating upwards, right, and this guy's accelerating down. So I have to be careful here, right? This M2A is actually negative. I have to denote that this A is going in a different direction in order for this to work. So I am going to put minus M2A over here. Okay? I'm going to get this out of the way. So that's key. If this guy is accelerating downwards, I need to make sure I take that into account in my force equation. Okay? All right. So now I have two equations, two unknowns. I want to find the acceleration of the system. Well, let me eliminate T. Okay? Over here, I can say that T is just equal to M1A, right, plus M1G. True story? Yeah. It looks good to me, right? So then all I got to do is take this T and put it in over here, right? So I get M1A plus M1G, that's my T, minus M2G equals minus M2A, right? I want to get my A's all on the same side so that I can solve for it, right? So that'll give me, this will give me M1 minus M2G. So basically, I kept these two guys, but I just pulled out a G from each of them because there's a common G, right? It makes my life a little bit easier. And then I can say that this is going to be, let me just give myself a little bit of room here. Okay, so this is going to be minus M2A minus M1A. Right? Okay, so now I can pull that A out, right? So I'll get negative M2 plus M1 times my A, right? All I've done is pulled out a minus sign and an A, okay? And I will have on this side M1 minus M2G, okay? So here's what I'm going to do. I'm going to go ahead and solve this equation for A, and I'm going to write it over here. So A equals, okay? I just divide both sides by this negative M2 plus M1, right? But dividing by a negative is the same thing as just like flipping the order of these guys, right? And if you guys want to just slow down, I'm skipping steps for speed's sake, right? But I'm just going to say that minus sign really just makes this M2 minus M1. Same thing, okay? Times G still, divided by M2 plus M1, okay? And I put in all my values, right? I put in my M2 equals 10, my M1 equals 5, again, my M2 equals 10, my M1 equals 5, right? Multiply by the 9.8 of G, and I get A equals 3.3 meters per second squared. There's a lot of steps here, more room for mistakes, so if you see a mistake, please let me know. But the moral of the story is that by making two free body diagrams on each of these objects, right, in this Atwood machine, right, and then putting those free body diagrams, the forces from them, into these two equations, okay, I am able to solve for two equations, two unknowns, eliminate t, and get the acceleration of this object, okay? There's many, many problems of these in the physics universe, okay? There's more in our textbook, and there's just more out there. If you guys want to explore, you know, how to solve Atwood machines, I recommend it. I feel like this is kind of the pinnacle of difficulty that I'll expect in this course for solving force or tension problems. But this is kind of like the bread and butter. Like, if you can understand this, you understand tension and forces, okay? So I recommend trying this again on your own, step by step, letting each step make sense. And when you can do this alone without my help, that's a good place to be, okay? With that said, the next slide, finally, is the very last slide, and it asks the question, how do we find the speed of a raindrop that falls on your head? Okay, I'll see you there.